All right, we're recording. Properties of integrals. All right. So they're just, properties of integrals are kind of what they sound like. They're just things when we see an integral that we can either automatically know the answer, have a shortcut for, or maybe make a slight adjustment before we actually do the integral. The first one is pretty simple. We are looking at an integral where both the lower limit and the upper limit are the same. So think back to your left and your right sums. What would delta x, or how do we find delta x when we're doing a left and right sum? I do care, because I asked, how do you find delta x?
This thing's called that equation. It's 0 over n.
It's 0 over n, right? Because the formula for delta x is b minus a over n, but in our case, we don't have b minus a, we have a minus a. And regardless of what that number is, if it's the same in both places, you've got a big 0. So when you go to do that Riemann sum, you're taking the limit as n goes to infinity of a sum that counts up, but every single thing in that sum is 0 plus something, or 0 times something, I should say. So you're basically just adding 0 and like the actual number 0, not even a number close to it, but the actual number 0 an infinite number of times, which is one of the reasons why the integral, if the limits are the same, is equal to 0. Again, fundamental theorem, we know that now, and that wasn't part of, if we had done this in the AP order, we wouldn't have had that spot right here, but you would just be doing capital F of A minus capital F of A, which is also the same thing minus the same thing, which is also 0. So in plain words, if the limits are the same, the integral is 0. Nothing to do there, no antiderivative to find. You may have noticed that this was kind of hidden in the fundamental theorem circuit. I believe the last problem was a really complicated integral, but you ended up plugging 3 and 3 in both of them. So you ended up with 0 as your correct final answer. Of course, I only have one of those papers, so maybe you didn't. Okay. Example 2. We have two integrals with the limits switched. The one on the left is from 0 to 2. We're going to write a left Riemann sum for that. The one on the right is from 2 to 0. We're going to make a right Riemann sum out of that. And we just want to see what the difference is here. And this is going to kind of prove why the limits are what they are, or why the property is what it is. So let's get the dust off. We've got the limit as n goes to infinity of the sum from k equals 1 to n. What's our delta x and our xk here? Start out with delta x. 2 over n. And what is our x sub k? Two k over n, yep. And I believe we want to do, since we're doing a left sum, we want to go from k equals 0 up until n minus 1. Boom. All right. So we've got 2 over n times 2k over n, but squared. Okay. All right, let's take a look at our second one, which is the same integral, but the limits are switched around. What's our delta x this time around? Negative 2 over n, right? And our x sub k, minus, yeah. Yeah, there's no negative in there one. You had me second guessing myself there for a second too. 2 minus 2k over n. So it's a plus delta xk. Oh, I'm sorry. I thought you just said plus. My bad. I thought you said, you're good. You had the right answer in the end. I just misinterpreted what you said. All right. So in this case, we have a right sum. So we're going to do the limit as n goes to infinity of k equals 1 to n. That's terrible sigma. Our delta x is negative 2 over n. And now we've got to do 2 minus 2k over n, but squared. Right. The thing that might not be completely obvious is that those two things represent the same numbers, but in reverse order. Okay? So here, when k equals 0, we are starting at 0 and squaring it. And here, when we get to the end, n, we'll end up with 2 minus 2n over n, which is also 0 squared, right? So those summations are actually the, sorry, I shouldn't say those summations, but the numbers that would happen in the summations that I have underlined in light blue, they would all be the same numbers, they're just being reversed. So the only difference between these two limits is the delta x, okay? And the only difference between the delta x is one's positive and the other one is negative. So yeah. The second integral is negative, but the rest is the same.
Is the area under a curve the absolute value of that?
That's what we're going to talk about in the next, we're going to talk about that next example. So you're going to have to be a little bit careful. We're going to talk about this in a couple different ones. We've only sort of looked at area moving forward, but now when you move backwards, the roles sort of reverse. So if you're traversing the x-axis backwards, then above the graph is going to be negative and below the graph is going to be positive. So direction is going to be important. Now we're going to see that when we get down to example 3. But in plain words, if you switch the limits, the value of the integral changes signs. So what Jack asked is exactly what's going to happen here in example 3. This is actually 2 properties in one here. It's kind of a twofer. It's going to take a look at property 2 and jump into property 3, which probably is of all of them, this property after this one is probably the least important. So when we look at example 3, it might seem pretty simple at first. It is. Calculate the integral by finding the area under the curve. But you'll notice we're going from 6 to 1. So we are going from right to left. So that answer is still going to be the area under the curve, which is how much? 20. But since we're going backwards, we reverse the role of the signs. We end up with negative 20. Yep. And again, that's just because our delta x's are negative. When you think of this, if you were to think of this as a Riemann sum, everything has its signs. You know, the first delta x, if we were just doing a Riemann sum with 1, this would be a negative 1 times 4 rectangle. This would be another negative 1 by 4 rectangle. So the direction that you're moving is important, whether you're going up or down or left or right. It is just negative 20. It is correct. Yeah, it is. Yeah. All right. With that in mind, this is the one that I'd love if people remembered and actually used, but it seems like nobody ever does because everybody just uses the fundamental theorem with this one, but there's a shortcut to the fundamental theorem in this one. If you're integrating a constant, you are finding the area of a rectangle, right? I mean, think about what I said there. If you're integrating a constant, your graph is a horizontal line. And if you're going between two numbers, there's your rectangle. So the shortcut to this is just finding the area of that rectangle. That rectangle has a base of b minus a and a height of k. You don't need to find an antiderivative. You could say to yourself, hey, I'm just finding the area of a rectangle here. Will you ever actually do that? I don't know. If you just use fundamental theorem and make that kx, and then plug b minus a in for x, you'll get the same result. The integral of a constant is the area of a rectangle. With b minus a height k. This one, so unimportant that I won't even make a card for it. I was about to write a third card today and I said, no. Cool. All right. Write out a Riemann sum using 4 subintervals on 1 to 5 while I pick up the phone. Raynak. Hey, good, how are you? Yeah, she is. Right. Right. Gotcha. Wow. Okay. That's it? It's just one? It sounds, yeah. That'll be easy. Look at this. That'll be easy. All right. No problem. All right. All right. I think sometimes when you're given a function, the easiest way to do that is just kind of make a table, right? Our x and our f of x, we go from 1 to 5, 4 subintervals. So 1 to 2, 2 to 3, 3 to 4, 4 to 5. Yay? Yeah. And then that makes f of x 1, 4, 9, 16, 25. No. So right Riemann sum is basically the intervals are going to be 1. So let me hit pause there. I was avoiding saying certain things. So for completeness, each number in our right sum should get multiplied by 1 because that's the width of the interval. So we end up with 4 plus 1, or 4 times 1 plus 9 times 1 plus 16 times 1 plus 25 times 1. It's a right Riemann sum, right? With 4 subintervals, so there should be four numbers. So when you're doing a right, you skip the furthest left number. With a left Riemann sum, you would skip the furthest right number. So I'm going to add 9 and 16 first because that's 25. Then I'm going to add 25 and 25 because that's easy. That's 50. And then I'm going to add 4 to give me 54. So I game planned before I brute forced that mental math and made my life easier. All right. Let's do the same table for x and f of x. We're going to get 1, 2, 3, 4, 5. And I am going to, instead of doing the math, especially for the purpose that I want to show here, we just have 3x squared. So the f of 1 is 3 times 1. The f of 2 is 3 times 4. The f of 3 is 3 times 16, 3 times 25. Yep. Which means that my Riemann sum here is going to be 3 times 4 times 1 plus 3 times 9 times 1 plus 3 times 16 times 1 plus 3 times 25 times 1. And again, those ones there just for emphasis that we are finding a Riemann sum. The widths are 1. And sure, I could do all of that mental math, but I have 4 things being added. 3 is a factor of all 4 of those things. So why not just write 3 times 4 plus 9 plus 16 plus 25? Because I already know that that's 54. That's 150 plus 12, 162. Boom. Think for a minute, because this is definitely going somewhere, because this is exactly the same thing. And I even have words. I don't know if we'll get to actually, we won't get through all the properties, but I will go to the follow-up to what we're going to look at in these next couple things. When we took derivatives, there were things that worked well and there were things that worked not so well, right? The things that worked well were constant multiples, adding and subtracting, and horizontal shift. Constant multiple is the same deal here, right? Do I need to solve a brand new integral if I want to integrate 3x squared, but I already know the integral of x squared? No, I just need to multiply by 3. So the same things that work for derivatives work for integrals. So the integral from a to b of k f of x is k times the integral a to b of f of x dx. You can pull or factor out a constant multiple from an integral. Boom. When we're actually doing functions, like if I have a function 3x squared, we don't think about this property as much because you just work. You just do 6x squared when you do, or that's taking a derivative. You just you just work with the constant multiple as part of the problem. But when you have a table, when you have a graph that you're doing, that would be an example of when you pull this out. Okay, so that's the last property I want to go over today. Let's take a look at what I have here down at the bottom of, I believe, the next page. Because this follows basically what the next several things are. An important note. Keep in mind, we had the product rule and the quotient rule. Think about the times that you had xy written and you wrote dx dt, dy dt, and I said, no, that's wrong. You didn't use the product rule. Think about that time you had a quotient and you just took the derivative of the numerator and took the derivative of the denominator, and I said, no, you need to use the quotient rule. Integrals are more complicated than derivatives, so that same thing, those same things apply here. We are never going to be able to split by multiplication, by division, exponents, anything like that. It's all more complicated. We're going to learn some of the techniques to deal with quotients in AB Calc. And as a matter of fact, a product isn't even part of the AB Calc curriculum. Okay, so this sort of an integral right here is only for BC. It is also a integration B integral, so we will learn it at some point because we kind of have to for that one. It's the only real BC topic in there. But integration is reversing a process, and it is way, way more complicated. So right now, these properties that we're talking about are the only things that we know how to do. And any of the things that didn't work for derivatives, I guarantee you, are not going to work for integrals. Okay, so just keep that in mind. If you do this, I'll probably write A8 on the paper, A and a bunch of H's. All right, as I sometimes do. All right, cool. We'll pick up there on Thursday. Quiz tomorrow, tutoring today. Yeah.
I learned how to do use substitution from TikTok.
All right.
And no joke, I had a dream that I did it.